We are doing WAKISSHA Math Paper 1. We are doing item 2, 2026 for Senior 6. A manufacturing enterprise has embarked on a strategic upgrade to optimize its industrial liquid filtration and power control systems. To ensure operational efficiency, the management team must make critical decisions regarding expansion, procurement, and system stability. During the initial phase, the company planned to increase the number of filtration units installed annually. In the first year, 10 units were installed. This is first year. They installed 10 units. The second year, 20 units. I'm summarizing my work. 20 units were installed. The engineer planners agreed that the annual installations would continue to grow by the same constant ratio. However, the operation budget can only support the expansion if the total number of units installed during the first 10 years does not exceed 12,000. Now we are going to first of all find out, after the first 10 years, how many units are installed. So they are telling us part A, to help the planning team establish if the installation program is financially sustainable. Now we are going to get that common ratio, or that, we are calling it a common ratio because they are saying it is increasing by a common ratio. So if this is my first term, my second term is 20, of course I'll have other terms, and they are saying there is that common ratio. So how do I get it? I get this 20, I divide by 10, and I'm calling it R, which is going to be 2. This is the common ratio. And my first term is, I'm starting with the 10 units. Now, they have said that before I proceed to the other parts of this question, they have said that the budget can support if the total number of units installed during the first 10 years. Now we are going to consider, this has been first year, second year. If there are 10 years, you can do it manually, but we can also go ahead and find that after 10 years, what shall we have? We are going to get the total number of units. So the sum, this is a geometric progression. Sum of a GP where R is greater than 1 is given by A into R to the power n minus 1 over R minus 1. We are saying this is possible if R is greater than 1. There are cases whereby R is less than 1, then we shall use the other one of saying 1 minus R to the power n over 1 minus R. Now, this is just a matter of substituting. S, there are 10 years. My first term is the 10 units into the common ratio, which is a 2 to the power 10 minus 1. This formula can be proved, 10 minus 1. Then you just need to use your calculator and simplify to get the necessary answers. I'll start with this one, 2 to the power 10, which is 1024, 1 GB. 2 to the power 10 minus 1, then divide by, this is going to be a 9, then I multiply, R is, it is not 10, it's a 2, sorry. It's our R is a 2, not 10. So it is 2 to the power 10 minus 1, which is going to be 1023. 1023. This is a 1, so it goes. Then times 10, which gives us 10,230. So this will be the sum of units installed after 10 years. So they told us that, however, the operational budget can only support the expansion if the total number of units installed during the first 10 years does not exceed 12,000. So we are saying that after 10 years, we just have 10,000 units. So I'll conclude with part A, since they want me to help the planning team establish the installation program if it will be financially stable, suitable, sustainable, I'll say yes. It is a conclusion is a must. It is financially sustainable. It is financially sustainable. You give a reason. The reason is simply because the number of units after 10 years will be less than the one that was given, which was 12,000 units. Then we proceed to other paragraphs. They have added on some information and said that to maintain the production line, the procurement office purchased three types of electrical components: voltage regulators, sensors, and transformers. The office received supplies from three different industrial vendors in thousands of dollars. That is so per amount, as shown in the table. So we have voltage regulators, voltage regulators, let me call them V, voltage regulators, we have sensors, then we have transformers. Voltage regulators, let me define them by X, sensors, let me define them by Y, then these transformers, let me define them by Z from these vendors, alpha, beta, and gamma. But it is in $1,000, that shouldn't be forgotten. Then from alpha, they got two of these. So I'm going to write out the equations. They got two of the voltage. From the sensors, they got one. So that is 1 times Y. Then transformers, they got 3 Z. This one will equal to the total cost was 45 US dollars, but in thousands. When they went to beta, they got 3 of the voltage regulators, they got 2 of the sensors, 2 of these ones, then they got 1 of the transformer, which is Z, and the total is a 35. Then when you go to gamma, they got 1, which is X of the voltage regulators, they got 3 sensors, which is 3Y, then they got 2 transformers, which is 2Z, but after adding all of them, the money spent was 40. I know there is a question here that they need. The finance department needs to determine the individual cost of each component. Having bought it 2, 1, 3, and they spent 45, and having bought 3 VRs, 2 sensors, and 1 transformer, spending 35. How much was spent on each? So we are going to solve these 3 simultaneous equations. They want us to see whether an allocated budget of 200,000 US dollars is sufficient to purchase 5 of these, 4 of these, and 6 of these. So before we start, let us get the amount. So I define my unknowns and I say that let X be the cost for the regulators, let Y be the cost for the sensors, and let Z be the cost for the transformers. And I'm going to solve these 3 simultaneously. This is equation 2, equation 3. Now I'm going to first deal with this. Then I can eliminate the Y. How? I can rewrite it as, I'm going to use elimination. 2Y plus 3Z is equal to 45. Then I also have 3x plus 2y plus z is equal to 35. If I want to eliminate this y, I'll come to this side. I multiply, this is going to be 1. I multiply with the 2, okay, with the 1. Then after multiplying, I'll have 2 times x, which is 4x, 2 times y, 2y, 2 times 3z, which is 6z, then 2 times 45, which is going to be equal to 90. Since I'm multiplying with the 1, I maintain 3x plus 2y plus z is equal to 35. I subtract. This gives x, this gives 0, plus this gives 5z is equal to, then this is going to give me, it is 55, 90 minus 35, it's going to give 55, and I'm saying this is equation 4. I dealt with this and eliminated y. So still I can eliminate, now you're supposed to eliminate y still in the other pair. Still I can say this one and this one here. I eliminate y. So I'm going to rewrite x plus y plus 3z is equal to 45. Then now I'm writing this x plus 3y plus 2z is equal to 40. For me to eliminate y here, I need to multiply with the 3. Then this I multiply with the 1 such that I'll have a 3y minus 3y. Then I need to first of all multiply through. I have 6x plus 3y plus 3 times 3z, 9z is equal to 45 times 3 is 135. Then this is going to remain as it is, x plus 3y plus 2z is equal to 40. I subtract still, this is going to give us 5x, this is a 0, then this is plus 7z is equal to 135 minus 40 will give 95, and I can call this equation 5. Now I have this and this. I need to eliminate. So I'm writing equation 4, which is x plus 5z being equal to 55. Then I also have 5x plus 7z, which is equal to 95. I can eliminate the x. How? Multiply with the 5 that is here, then you multiply with the 1 here, and it will give me x times 5, which is 5x. 5 times 5z gives 25z. This is equal to 55 times 5 is 275. Then this, since I'm multiplying with the 1, it stays as 5x plus 7z is equal to 95. I need to subtract still such that the x leaves. I have a 25 minus 7 giving me 18z is equal to 275 minus 95, which is 180. Then I divide by 18. So I've got z as 10. Then when I get z as 10, I can come to equation 4, and I get x. We say that x is going to be equal to, when the 5z goes the other side, it will become 55 minus 5 times z, which is 10. So my x value will be, because this is 55 minus 50, it is going to be 5, but those are dollars in thousands. Then I go to the initial equation to get x. Let me use this one that just has x. Sorry, to get, I've got x, I've got z, I need y. Let me use the first one. So I'll say 2 times x, which is 5, then plus y that I'm looking for, then plus 3 times z, which is 10. This should equal to 45. Then when computing, I'll have a 45 minus 40, because this is 30 plus 10, that's 40. So 45 minus 40, y will be 5. This implies that the cost for VR goes for I conclude VR goes for 5,000 US dollars. Then this one goes for 5,000. This goes for 10,000. But there is a condition they gave us that we are supposed to follow. They said that they want to define the individual cost. So individual cost, let me first define the individual cost of each. Individual cost, the VR was the voltage regulators. Therefore, the voltage regulators, this one's cost, we defined it as X and it is costing 5, it was in thousands, so 5,000 US dollars. Then we go to the sensors, the cost of sensors cost, sensors are Y, and we are saying Y is also 5, but it is in 1,000 US dollars. Then finally, the transformers, this one's cost 10,000 US dollars. They continued and tasked us to see if the budget is sufficient, if they bought 5 voltage regulators, 4 sensors, then 6 transformers. They want to see if the 200 US dollars are sufficient. So we are going to say 5 times the 5,000, the cost of a VR plus 4 times the sensors, which go for 5,000, then plus the 6 multiplied by the 10,000. We want to see if it is less, then it will be sufficient. 5 times 5,000 plus 4 times 5,000, then plus 6 exponent 4. We have 105,000 US dollars. Will it be sufficient? I say yes, it will be sufficient. Reason being, 105 US dollars that they have told us is less than the 200. So the budget is there, having 200, and these ones are just costing this amount of money. So I conclude like that. Still the same item is still continuing, and they are telling us that in the final phase of the project, a complex automation system was implemented to manage control signals. The reference signals of the system is Z0, this is the control, is equal to 2 plus 3i. Then they added on and said, and the control signals are modeled by the equation z cubed minus 3z squared, then plus 7z minus 5 is equal to 0. The automation system will remain stable and operational if the modulus of the difference between the reference signals and each control signal, they have given us the magnitude of Z0 minus the Z, which we are going to get from here, should be less than 4 units. Now Z0 we have the reference signal, the control signal, but this is the reference signal of the system. But the control signals are going to come from this one here. This is a cubic complex equation which we can get its factors, and we get the difference, then the modulus. We test if this is valid. So what we are going to do is, like for any other polynomial, this is going to be treated like a polynomial. We are going to first test and see what are the roots of this equation. You can use your calculator or you can even do it manually. Just using values that are around 1, -1, 2, -2, and 3. Let me start with the 1. If I substitute in a 1 here, I'm going to have 1 minus 3, then plus 7 minus 5. Is it equal to 0? So this is 1 minus 3, which is a -2, plus 7, that's a +5, minus 5 is a 0. So it implies that actually z is equal to 1 is a root. After testing, you can just test that using these numbers that are closed. So I'm saying z is equal to 1 is a root. Why am I saying it's a root? Because it is satisfying the equation. If I put in 1, I get a 0. So I need to get the factor by taking the 1 this side, becomes z minus 1 is a factor, and at the same time I'm saying it's going to be a divisor. It's going to be a divisor. So I'm going to do long division. I have my divisor, which is z minus 1, and it is dividing this. What am I doing? I'm trying to reduce it. This is z cubed minus 3z squared plus 7z minus 5. Z cubed divided by z, I get z squared. Then z squared times z, I have z cubed. Z squared times -1, negative z squared. I subtract. When I subtract, this is a 0. Then I have a -3z squared minus z squared. This gives me -2 z squared. Then I bring the plus 7z, then minus 5. Still I divide -2z squared divided by z. What I'm doing is I'm reducing the polynomial which is having a degree 3 to degree 2, which I can easily solve. This divided by this, I get a -2z. -2z times z, I get a -2z squared. Then a -2z times a -1, I get a +2z. Still I subtract. This goes, I have a 7z minus 2z, which is going to give me 5z, but I have a -5 left there. Of course, some people say there is a +0, then they say -5 minus 0, which doesn't affect us. Then plus 5z divided by z gives a 5. Then 5 times z, 5z. 5 times -1, -5. So I subtract. Now, this is going to give a 0 because we said z minus 1 is a factor. So if you get a remainder which is not a 0, then there is an error made. What does this mean? This means that this is z we are seeing here, z cubed minus 3z squared plus 7z minus 5 is the same as z minus 1 into z squared minus 2z then plus 5. If you open brackets, you'll get back to this. Now, we have got one z. We need to get to the rest of the z values from here. This is a quadratic equation. Z squared minus 2z plus 5 is a quadratic equation if I'm to equate it to 0, because all of this was equated to 0. If I'm equated to 0, I'll have z from the quadratic formula of x is equal to x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. This is what I'm going to use here. Now we are not in x, we are in z. Z is equal to a negative b, which is a positive 2. Negative 2 is a positive 2. Plus or minus square root of b squared, which is going to be negative 2 squared, giving us a 4. Then minus 4 times a, which is 1, then times c, which is 5, over 2 times 1, that is the 2a. Then z is equal to 2 plus or minus the square root of this is going to be 4 times 20, start with multiplication. Sorry, 4 times 5 is 20. 4 minus 20, the negative 16 over 2. Now, since we are looking at complex numbers, it is only in complex numbers that we can get the square root of a negative. So it's going to be equal to 2 plus or minus the square root of a 16 is 4. Square root of negative 1 is I. So this is 4I over 2. I can divide through by 2. Then I have Z1 being equal to 1 plus 2I. Z2 is equal to 1 minus 2I. If I start with a plus, I have this. If I go to the negative, I have this. Divide by 2 here and here. This 2 divides this one and this one here. Not only here. 2 divided by 2, 1. 4 divided by 2, 2. Then we have our Z3. From the zero rule, having brackets equated to 0 is the same as getting a given bracket equal to 0 and the other bracket. So if I get this bracket and equate it to 0, my Z3 will be 1. But now they said for the system to be efficient, the magnitude of Z naught, which they gave us as the reference, minus Z naught minus Z should be less than 4 units after getting the magnitude. Now the task we are left with is finding Z naught minus Z. So I'm Z1 is 1 plus 2I. So I'm going to follow this. They said Z naught minus Z. My Z naught is 2 plus 3I minus Z. I'm using Z. Now this is Z1, which is 1 plus 2I. But they say the magnitude should be less than 4. So this is equal to, if I open brackets, I'm going to skip some steps. I open brackets, I'll have 2 minus 1, which is a 1. Then I'll have a 3 minus 2I, which will give me I. So getting the magnitude, it will be, this is squared plus 1 squared, the coefficient of I. We don't square I. So this is just root of 2. Root of 2 is not greater than 4. It can't. Root of 2 is 1.41. Root of 2 is 1.4142. So since this is less than 4 units, this is a yes for us. Let us test for Z2. Z2 is equal to 1 minus 2I. The magnitude of Z0 is 2 plus 3I, then minus, opening brackets is so paramount, Z2, which is 1 minus 2I. This is equal to, this is going to be a 2 minus 1, which is a 1. Then 3I minus 3I, which gives us 5I. Since they are under magnitude, I'll just say square root of 1 squared plus 5 squared. That is the root of 26. And it is greater than 4. 5.0990. It is greater. So this is no. They said it will only be possible if all of them are less. This is a no. Let me test the final one, which is Z3. And Z3 we said it was just a 1. Still we use the magnitude of Z0 minus Z. Z0 was given as 2 plus 3I. Then I subtract off a 1. This is just having real values. And this is equal to the magnitude of 1, 2 minus 1, which is a 1, then plus 3I. Magnitude of this is going to be 3 squared plus 1, which is 10, and the root of 10 is just a 3.162. So here it is possible. But now, according to the question was very clear. They said that the automation system will remain stable and operation if the modulus of the difference between the reference signals and each control signal Z0 minus Z in the magnitude is less than 4 units. This would qualify, but because this doesn't qualify, we say the automation system will remain unstable. Therefore, the automation system will remain unstable. The reason because there is a magnitude which is greater than 4 units. Thanks for watching. Hey, the question was asking, I answered before even reading the question. The question was asking, at times if you read a given pattern, you start attempting, it becomes easy. It was saying, advise the management team to take well-informed decisions as they undertake the remaining 2 projects. The first project was to see if the money will be sufficient to buy the others. Yes, it was sufficient. Then the last one was automation, and we have seen it will not be successful. Thanks for watching. We meet in the next video, item 3.